This video is on Hooke's laws and elastic potential energy. I'm Mrs. Estock. Let's get started. Hooke's law states that the change in spring length from its equilibrium position is in direct proportion to the force applied to it. Or in other words, if you pull on a spring, it will stretch a certain distance. The genius mathematician / physicist that came up with this law is named Hooke. And if we put it in formula form, it looks like this. The spring force, Fs, is equal to a spring constant, K, multiplied by the distance the spring is stretched, X. Force, like any force, is measured in newtons. The distance stretched is measured in meters, and the spring constant has units of newtons per meter. So, what does Hooke's law mean? Say that you have a spring that starts out not stretched at all. So it's in its what we call equilibrium position. It's not stretched or compressed, it's just kind of chilling there. If you pull on that spring or push on it with a certain amount of force, you're going to cause it to stretch a certain distance x from its equilibrium position. And the amount of force compared to the distance stretched is in direct proportion. So let's say we double the amount of force pulling on this spring downward, that in turn will double the distance that it is stretched. If we apply Hooke's law to a practice problem, it would look something like this. What force is required to stretch a spring with a spring constant of 50 newtons per meter, a distance of 2 meters? Let's use Hooke's law to solve for the spring force. Spring force is equal to spring constant times distance stretched. 50 newtons per meter, times 2 meters gives us a spring force of 100 newtons. Or in other words, it would take 100 newtons of force to stretch this spring 2 meters. So in Hooke's law, it might be easier to imagine force and distance, but spring constant is probably a variable you have not seen before. Spring constant is represented with a lowercase k. As we said before, it's measured in newtons per meter. But what does that really mean? Well, it's a constant for a particular spring telling you how many newtons is required to stretch it a certain distance. In other words, it's a number that describes or represents the object's stiffness or rigidity, how rigid the spring is, or how easy it is to stretch or compress. The bigger the K value, or the bigger the spring constant, the more rigid it would be and the harder it would be to stretch or compress. So a spring with a big K value would be really difficult to stretch or compress. K is a value that also depends on the physical properties of the spring itself. What type of metal is it made out of? How thick is it? What is the diameter? How many coils are there? What is the overall length of the spring? These factors would affect the value of K, making it either more or less rigid. And again, K is here in our Hooke's law equation, the variable K that I have circled. And in the picture, I have two springs, spring 1 and spring 2. Could you guess which one has a larger K value? If you guessed 2, you would be right. Spring 2 would be more rigid because it's thicker and it has a larger K value. For those 2 springs, let's say that we added a 50-gram mass to each so that both are feeling the same spring force pulling downward. Since spring 1 has a smaller spring constant, it would stretch more given the same size force. Since spring 2 is more rigid and has a higher spring constant, the same size force would cause it to stretch less from its equilibrium position. So here is an example of how 2 different spring constants would result in 2 different distances stretched given the same size force. Sometimes you'll see Hooke's law represented graphically. If you graph force versus elongation distance, or distance stretched, the slope of that line will be equal to the spring constant. So in the example graph, which spring has the largest spring constant? Spring A, B, C, or D? The correct answer is spring A. And that's because line A has the steepest slope. Again, the slope represents the spring constant. Or in other words, for the same amount of elongation or the same distance stretched, spring A would require more force to stretch it that same distance. Now, be warned, Hooke's law works for some situations, but not all situations. So here's a little peek behind the curtain, if you will. In the diagram, the red line on the graph shows how spring force theoretically varies with elongation distance according to Hooke's law. So this represents a linear relationship for both elongation or stretched or compression distance. However, in the real world, this is not what we typically see. Typically, elongation and compression for springs follows Hooke's law, but only for a certain amount of stretch or compression distance. When an object reaches a certain point, it's maybe overstretched or overcompressed, that gray dotted line represents the actual plot of spring force that we would see in the real world. We can see the relationship turns from something linear to something more curved or non-linear in nature, let's say. So just beware that springs supply a varying amount of force. In other words, the more a spring is stretched, the more force it's going to apply back. That means that Hooke's law is really only valid for a certain portion of the curve. And also for this reason, we cannot use the work equation, work equals force times displacement, with springs. This formula is only valid for a constant amount of force. And because spring force can vary, in other words, because spring force can be nonlinear, you cannot use that work equation to calculate the energy stored in springs. Instead, we need to use a different equation to calculate the potential energy stored in a spring. In other words, the work done to stretch or compress a spring is equal to however much potential energy is stored within that spring. And for that calculation, we're going to use the following equation. To calculate the elastic potential energy stored within a spring, we're going to use the equation 1/2 times spring constant times distance stretched or compressed squared. In other words, when a force, Fs, spring force, stretches or compresses a spring by some distance x, the work done is stored in the spring as elastic potential energy. And we can calculate just how much elastic potential energy is stored using this equation, where elastic potential energy, like all other forms of energy, is measured in joules. Spring constant is still measured in newtons per meter, and the distance stretched or compressed is measured in meters. With this equation, we can see that there is a quadratic relationship between distance stretched or elongation and potential energy. So if you have a potential energy versus elongation graph, the shape of that graph would be quadratic in nature. Let's try one final practice problem using our new equations. Suppose a mass rests on a frictionless horizontal surface and is attached to a spring as shown in the diagram below. Then, suppose the spring is stretched 0.5 meters from its equilibrium position. What is the force exerted by the spring on the 2-kilogram mass if the spring has a spring constant of 50 newtons per meter? In order to solve for force, we're going to use Hooke's law, where spring force is equal to spring constant times distance stretched. If a spring with a spring constant of 50 newtons per meter is stretched half a meter, it would require 25 newtons of force to do so. Next, how much energy is stored in the spring? Well, by stretching that spring half a meter, you are storing a certain amount of elastic potential energy in the spring. To calculate how much energy is stored in the spring, we'll use our equation PES, or spring potential energy, is equal to 1/2 kx squared. 1/2 times 50 newtons per meter times 0.5 meters squared gives us a stored potential energy of 6.25 joules. Lastly, if the mass is then released and allowed to slide horizontally, how fast will it be moving when it passes through the equilibrium position? For this problem, let's think about this in terms of conservation of energy. Ask yourself, what kind of energy transformation is happening? Initially, the energy is stored as elastic potential energy, but as it returns to its equilibrium position, that potential energy is transformed into kinetic energy of motion. So here we can say that the initial potential energy stored in the spring is equal to the final kinetic energy as it moves through its equilibrium position. We've already solved for the initial potential energy stored in the spring, but we're looking to solve for how fast it will be going. If we take our kinetic energy equation, 1/2 mv squared, we could solve for how fast it's traveling, or the speed of the mass. Now we can plug in our values. We calculated the stored potential energy in the spring as 6.25 joules, and we know the mass is equal to 2 kilograms. So if we solve for V, we get an answer of 2.5 meters per second. So that's how fast the mass is going once all of that stored potential energy is converted to kinetic energy.